So now that we have at least a sense for Newton's three laws of motion, let's consider a falling object. Consider dropping an object from the roof. Okay, so dropping an object from the roof. And you know that it's going to go from 0 meters per second to going to go faster, but I don't know if you knew that for every 1 second it falls, actually it's going to go faster and faster, 10 meters per second. So it looks like this. So here we have, it's not a, yeah, it is a ball. So here it's a velocity 0. In 1 second, it's 10 meters per second. In 2 seconds, it's 20 meters per second. And if it were able to go ahead and fall another 3 seconds, of course, it would be about 30 meters per second. T is equal to 3 seconds. Velocity equals 20 plus another 10. 30 meters per second. Now you may have learned this as this is what we call the acceleration due to gravity, and it's usually kind of a symbol little g, and you may have learned it 9.8 meters per second for every second it falls. So it's 9.8 meters per second or per second squared. But in this course we're going with 10 meters per second, which is about 9.8. But the point is that it's going faster and faster and faster, and of course we call that going faster and faster and faster, accelerating. And as we've been talking about, Newton's laws say, hey, if something is accelerating, then there must be some force making that happen. And of course that is the force of gravity. Gravity, we're going to take a look at it here with in a minute with Newton's equation, universal equation of gravity, but it is just a mutual attraction between two objects based upon their masses and how far apart they are from each other. So related also to Newton's laws of motion is this concept of momentum and force. Now, I mentioned inertia when I talked about Newton's first law, that an object at rest will stay at rest, an object in motion will stay in motion with the same motion unless acted upon by an outside force. Momentum specifically can be calculated by taking the mass of an object times its velocity. So if I have, for instance, a bicycle going down the road at 35 miles per hour, okay, it has a certain mass, and if I could draw a bicycle, I would, going 35 miles per hour. But instead of a bicycle, let's go ahead and substitute in that. Let's substitute a Mack truck going the same speed. Okay, so you can tell that the Mack truck weighs a lot more, and so actually the Mack truck has more momentum. That's kind of how that works. So momentum of the Mack truck would be in the same direction that the truck is traveling. And of course it would have a certain, what we say, magnitude that is very high based upon its mass. Then consider this. If you want to change the momentum of an object, okay, you can't change the mass of an object, but by golly, you can change its velocity. So if you change its velocity, you are what? Changing its speed. If you change its velocity, excuse me, you're either changing its speed or its direction, and that is a type of acceleration. So changing momentum requires acceleration to occur, and it means that a force must be applied. So we've kind of come full circle and actually kind of linked then back into if you're on top of a roof and you drop something from the roof, and it goes faster and faster and faster for every second it falls, it's going to go faster about 10 meters per second. The fact that it is going faster means that some sort of force is causing it to accelerate. And of course that force is force of gravity. Now before I move on, I guess I should say one thing, and I think your textbook addresses this. There is something called terminal velocity, and terminal velocity just simply means that if you have an object that is falling, okay, based upon kind of the aerodynamics of the object, it will reach a terminal or velocity, a maximum velocity. But that's only because it actually has air that it's falling into. So these are my air particles. Okay, so within the absence of air, there is no terminal velocity.